Thanks to my Patreon members for supporting this channel. You can support this channel by going to my Patreon page. Link is in the description below. Now back to the video.
A group of researchers from Artificial Intelligence Research Institute released a new AI paper titled 3GRAPM, Combining Semantic Graphs and AI Large Language Models for 3D Scene Understanding. In recent years, the interplay between artificial intelligence, AI, and three-dimensional 3D scene understanding has taken significant strides, particularly in the realm of embodied intelligent agents, robots or AI systems capable of interacting meaningfully with their environment. A crucial aspect of such interaction is the ability to interpret and respond to natural language queries about a 3D environment. Imagine asking a robotic assistant, identify the mug on the table, or to explain what objects are near the sofa. These tasks, which seem simple to humans, demand a sophisticated combination of computer vision and natural language processing capabilities. The paper titled 3GRAPM, Combining Semantic Graphs and Large Language Models for 3D Scene Understanding delves into precisely this challenge. The authors propose a novel approach called 3GRAPM, which combines the strengths of 3D scene graphs, structured representation of objects, and their relationships in a 3D space, with the reasoning and language understanding capabilities of large language models, LLMs. This essay explores the key ideas, methods, and implications of their work, offering insights into its innovative approach to 3D vision language tasks. Before diving into the specifics of 3GRAPM, it is essential to understand the broader problem of scene understanding. Scene understanding in the AI context involves interpreting and modeling an environment by identifying objects, their properties, e.g., color, size, or material, and their spatial relationships, e.g., above, beside, or within. This task is crucial for numerous applications, such as robotic navigation, augmented reality, and interactive systems. The 3D world scene understanding becomes more complex due to the additional spatial dimension and the intricacies of point clouds or 3D reconstructions. Unlike 2D images, which present a flat representation of a scene, 3D data encapsulates depth and positional information, making it ideal for applications that require real-world interactions. For AI systems to respond to natural language queries about such environments, they need to connect the dots between visual data and linguistic expressions. Traditional approaches relied heavily on handcrafted rules and domain-specific algorithms. However, the advent of LLMs trained on vast amounts of text data has revolutionized natural language understanding and reasoning, opening new possibilities for integrating 3D scene data and language. At the heart of 3D scene understanding lies the concept of a 3D scene graph. This representation serves as a compact and structured model of a 3D environment, capturing information about objects, nodes, and their semantic relationships. Edges. Instance, a scene graph might depict that a chair is beside a table or that a lamp is on a desk. By incorporating both object properties and relationships, scene graphs provide a holistic view of the environment. Scene graphs have demonstrated significant potential in various applications, such as navigation, object search, and interaction. However, traditional methods often focus solely on spatial relationships, e.g. coordinates, neglecting the semantic richness of these connections. This limitation hampers the ability to answer nuanced queries that depend on understanding object roles or abstract relationships. Authors of the paper address these challenges by introducing 3GRAPM, a method that builds learnable representations of 3D scene graphs. Their approach integrates semantic relationships between objects and provides these representations as input to LLMs, enabling them to tackle 3D vision language tasks effectively. There are a few contributions of 3GRAPM. Incorporation of semantic relationships. Unlike existing methods that prioritize object coordinates, 3GRAPM emphasizes the semantic connections between objects. Example: instead of simply recognizing that a mug is located at certain coordinates, the system understands that the mug is on the table and beside the notebook. Learnable representations. The method generates embeddings for each object in the scene, capturing its properties and relationships. These embeddings are structured as a sequence of triplets, e.g., object-tone, relation, object-to, enabling LLMs to process them as input tokens. Efficiency through k-nearest neighbors, optimize inference speed. The authors use a k-nearest neighbor approach with a distance filter, reducing the number of tokens required to describe the scene while preserving meaningful relationships. Integration with LLMs. The embeddings are mapped into the LLM's token space, effectively translating the scene graph into a format that the LM can reason about. Fine-tuning techniques like LoRa, low-rank adaptation, further adapt the LM for 3D tasks. The effectiveness of a 3D grapple is demonstrated across several challenging tasks. 3D referred object grounding. This task involves identifying a region in a 3D scene corresponding to a natural language query. For instance, the ELA system might locate the red chair next to the table. 3D grapple achieves significant performance improvements on benchmarks like ScanRefer and Multi-3D Refer. 3D scene captioning. Here the goal is to generate descriptive captions for objects in a 3D scene. The method outperforms baseline approaches on the scan toolcap dataset, highlighting its ability to produce detailed and accurate descriptions. 3D visual question answering. This task requires the system to answer questions about the scene, such as what is on the desk. The inclusion of semantic relationships enhances the system's reasoning capabilities, enabling more precise and context-aware answers. The authors report state-of-the-art results, with notable improvements in accuracy and quality metrics compared to existing methods. While 3D grapple marks a significant advancement, the authors acknowledge certain limitations. Resource consumption. The method's reliance on graph edges can lead to increased computational requirements as the number of relationships grows. Striking a balance between performance and efficiency remains an ongoing challenge. Robustness to imperfections. Real-world 3D data often contains noise or errors in object segmentation. Developing methods to handle such imperfections will be crucial for practical deployment. Token optimization. Reducing the number of tokens required to encode object relationships without compromising semantic richness is a promising area for further research. The integration of semantic 3D scene graphs with LLMs represents a paradigm shift in how AI systems perceive and interact with the world. By bridging the gap between 3D data and natural language, 3D grapple opens new possibilities for applications ranging from robotic assistants to virtual reality systems. This work highlights the importance of capturing not just what objects are in a scene, but how they relate to one another, enabling more intelligent and context-aware interactions. As AI continues to advance, innovations like 3D grapple will undoubtedly play a pivotal role in shaping the future of embodied intelligence and human-AI collaboration. Thanks for watching, and I will see you in the next video.